Alright, so today we're going to cover two problems in linear algebra. We have two matrices A and B that belong to M2 of C, that is the set of 2 by 2 matrices with complex entries. The first problem is to prove that determinant of A plus B plus determinant of A minus B is equal to 2 determinant of A plus 2 determinant of B. The second problem asks us to show this relation here, determinant of I plus 2AB plus 3BA over 5 is equal to determinant of I plus 3AB plus 2AB over 5. Okay, so let's start with problem A. So problem A asks us, we have determinant of A plus B plus determinant of A minus B. Now, to show this equality, it'd be nice to use some sort of polynomial relation, which is usually what we end up having to do for the determinant. In particular, I'm going to use the determinant of A plus XB, okay? And the reason why I think to do this is because, well, mainly because I've seen this before, but because we have this plus and minus in front of the matrix B, putting a variable x there allows me to manipulate that plus or minus sign freely. Okay, well, if we write this out, this matrix, we just have A11 plus xB11, A12 plus B12, plus B21, and A22 plus xB22. Okay, so taking this determinant term by term, I notice that something very interesting is happening. Okay, excuse me, there should be an x in front of the B21 and B12 as well. X B21 and X B12. All right, so in particular, I'm going to look at the x squared term. Okay, so in front of the x squared, I'm going to have a B11, B22 from cross multiplication along this diagonal, and then from cross multiplication along the opposite diagonal, I'm going to have a negative B12, B21. Okay, and this we recognize to just be the determinant of B. And then ignoring the x term, because that's kind of all the cross terms, it's going to be a bunch of gross coefficients. I'm just going to call this Cx. And then the constant term is going to be, by the same logic, A11, A22 minus A12, A21, which is just the determinant of A. So I see that the determinant of A plus xb in M2C is in fact determinant of B times x squared plus some constant times x plus determinant of A, all right? And this is very useful for me. In fact, it immediately solves our problem because we recognize this symmetry if I plug in 1 and negative 1 for x and then add those two determinants together, the constant terms, or the x terms, excuse me, will cancel. So let's go ahead and do that. So we've just determined that determinant of a plus xb is equal to determinant of b x squared plus cx plus determinant of a. And so now determinant of a plus b plus determinant of a minus b is precisely equal to determinant of b times x squared, which is just, in this case, x is equal to, here x is equal to 1, and here x is equal to negative 1. Negative 1. And in both cases, x squared is equal to 1. Okay, so I'm going to get 2 times the determinant of b when I add these together. Now the cx terms, I'm going to have a positive cx from determinant of a plus b, and a negative cx from determinant of a minus b. And so those terms will cancel. And then I'm just left with 2 determinant of a. The constant terms will also add together. Okay, and this is precisely the relationship that we were trying to show. Okay. So that does the first problem. Now let's look at the second problem. It's a bit trickier. Okay, so I noticed that the problem they're asking me to show 2ab plus 3ba over 5 and 3ab plus 2ba over 5, they're symmetric. Okay, and they're symmetric about well, if they're symmetric about the expression determinant of I plus AB plus BA over 2, all right? And so for your reference, I'm going to rewrite the problem out here. So determinant of I plus 2AB plus 3ABA, excuse me, over 5 is equal to determinant of I plus 3AB plus 2BA over 5. All right, so this is what we're trying to show. Now, recognizing this symmetry, where like I plus AB plus B over 2 is kind of like in between these two terms that we're trying to show are equal, why don't we introduce another kind of polynomial? So why don't we introduce determinant of I plus AB plus x times BA minus AB? All right, and recognize that this is now a polynomial in x squared. So this is a function of x, and in fact it's a polynomial in x, so I'll call it p of x. And we'll notice that p of x is, at most degree 2, right? Because this x term, if we take the determinant of a 2 by 2 matrix, this x is only ever going to become an x squared, okay? So it's of degree less than or equal to 2. Now I really want to show that p of 2/5 is equal to p of 3/5, okay? I believe that's what I want to show. And yes, it is, okay? And this here, this term is when I plug in x is equal to 3/5, and this term is x is equal to 2/5, okay? So, again, I'm going to exploit symmetry here, and I'm going to go ahead and, instead of having to show this relationship, I'm going to recognize that if I can show p of 0 is equal to p of 1, well then I'm pretty much there, because I've shown symmetry about this crucial x equals 1/2, right? So as long as we show that the quadratic polynomial is symmetric about x equals 1/2, we're done, right? Due to the fact that we know that it's at most a quadratic. So I'll explain a bit more of that in a minute, but let's look at, we need to show p of 1/2 is the vertex of essentially the vertex of p, okay? And so why don't we just use p of 0, which is determinant of I plus AB, and p of 1, which is determinant of I plus BA. And these quantities are far easier to deal with. So in case you're not familiar, and you can go ahead and compute this by hand, but if I take the determinant of C plus lambda I, where C is a 2 by 2 matrix, then this is essentially an eigenvalue problem, okay? Where lambda is the eigenvalue, or actually the negative of the eigenvalue of the matrix C. And this determinant is going to be lambda squared plus the trace of C times lambda plus the determinant of C, okay? So this is just a natural fact that pops up in 2 by 2 matrix determinants, and like to fully remind you of that, just recognize that the determinant, this crucial determinant of C plus lambda I gives the eigenvalues of C. And in particular, if I really want to be safe, I should say determinant of C minus lambda I will give the eigenvalues of C, but they're very similar polynomials. And now a crucial fact is that the eigenvalues of C, let's call them lambda 1 and lambda 2, they satisfy lambda 1 plus lambda 2 is equal to the trace of C, and lambda 1, lambda 2 is equal to the determinant of C. And this is a fact that actually holds in higher dimensions as well. The sum of the eigenvalues becomes the trace, and the product of the eigenvalues becomes the determinant of the matrix. Okay. All right, so enough with that little review there. So here, going back to our situation, we have the determinant of I plus AB. This is just kind of like almost an eigenvalue looking determinant, except we have lambda is equal to 1. And so this isn't necessarily 0, 1 isn't necessarily an eigenvalue of AB, but it's going to have this same form, okay, of basically 1, and there should be, yeah. So it's basically going to have the form of 1 plus trace of AB plus determinant of AB. And this guy will have the form 1 plus trace of BA plus the determinant of BA. Okay? And so it turns out that inside of a trace, it's just a general fact that the trace commutes inside of its argument. So trace of AB is equal to trace of BA. This is a general fact about matrices. And also, the determinant more obviously commutes because determinant of AB is equal to determinant of A times determinant of B, which is determinant of B, determinant of A, which is determinant of BA. And so we see that in fact these two terms must be equal, okay, because the determinant will commute and then the trace will also commute in the inside of this expression like so. And so we recognize that in fact determinant of I plus AB and determinant of I plus BA are the same exact thing. And that tells us that P of 0 equals P of 1. Now we know P is of degree less than or equal to 2, but because we have found two values of P that are identical for distinct inputs, that means that P is P is of degree less than or equal to 2. P is either of degree exactly equal to 2, so it's either actually a quadratic, or it's a constant. And if it's a constant, then these two terms are trivially equal. If it's a quadratic, we've shown that if degree of P equals 2, then we've shown that since there's symmetry about 1/2, P must have a vertex at 1/2. Since P of 0 equals P of 1. And visually you can see this by if you just take a quadratic polynomial and you recognize that two values are the same, well then the vertex has to occur at their midpoint, namely in this case the midpoint of 0 and 1, which is 1/2. And that also tells us that anything equidistant from 1/2 must have the same value. In particular, P of 2/5 equals P of 2/3. So since P has a vertex at x is 1/2, then then we know that P of 2/5 equals P of 3/5 by symmetry about 1/2. And so that immediately solves the problem because this is P of 3/5, and this right here is P of 3/5, and this right hand side of this equation is P of 2/5. And so yeah, in both of these problems, let's just recall what we did here. In both of these problems, we've set up a relevant polynomial and then exploited the symmetries of that polynomial for 2x2 matrices. Okay, and so this is something that shows up kind of a lot, and it's just some useful trick to know in general for linear algebra.